Yeah, let me recapitulate a bit what I had discussed in the earlier session. I was covering non-metallic inclusions, which are known as NMIs. Then I had talked about, there are two basic distinctions. One is the micro inclusion, where the size is less than 10 micron, so more or less 1 to 10 micron range. So these are basically or essentially product of metallurgical processes. For example, deoxidation. Through deoxidation, whatever inclusions are generated, we can call them as indigenous non-metallic inclusions, and they are usually minor in sizes, smaller in sizes in the ranges of 1 to 10 micron. These are basically oxides, and from sulfur, sulfides can be formed. So, we can have sulfides also. They are also normally very small in size in this range, and then there can be complex oxysulfides, combination of sulfides and oxides. There can be of course different types of oxides. I am not only talking of only alumina, there may be different oxides like TiO2, titanium oxide, there may be a combination of oxides. So, from the metallurgical processes, whatever inclusions are getting generated, they are finer in size, normally in the range of 1 to 10 micron. And then I talked about exogenous entrapments, which are relatively large in size, much larger than 10 micron. This range is 1 to 10, and those exogenous entrapments are usually larger in size. Basically, where from they are getting generated? They are getting generated from the slag entrapment. Slag may be from ladle, from the tundish, from the mold. There can be reoxidation products, which are also exogenous entrapment. How reoxidation products are getting generated? When liquid steel is getting exposed to air, there is reoxidation. So, these reoxidation products are also normally larger in size. Then there may be refract erosion products. That means, erosion products from the refractory lining from the metallurgical vessels of say ladle or the tundish. So, there are refractory lining in all of these metallurgical vessels. So, the refractory erosion products are also part of the exogenous entrapments. So, these are the three broad genesis of exogenous entrapments, which are relatively larger in size. Then I talked about NMIs. They basically encompass sulfides coming from the sulfur of steel, oxides which is coming from the oxygen content at the final stage. Normally, if it is beyond solubility limit, there will be oxides. If the sulfur is beyond the solubility limit, there will be sulfides, precipitations, formation of sulfides, oxides. Now, I have also talked about the total oxygen in steel. Total oxygen has two components, one is the dissolved, another is the oxygen present as oxides. I have also mentioned that when you are properly deoxidizing the steel, killing the steel with aluminum for example, then the dissolved oxygen is very low, less than 5 ppm. So, most of the oxygen present in steel will be as oxide. So, the total oxygen content can give an indication of the oxygen present as oxide. So, therefore, total oxygen content after refining is normally taken as a measure of oxide cleanliness, because the dissolved oxygen is low. So, whatever total oxygen is present, we are assuming the majority of it is present as oxide inclusions. So, this total oxygen can be taken as a measure of oxide cleanliness in steel. Then we had also talked about what are the distribution of inclusion sizes. This is a very important concept. When we call up clean steel, it is not free from inclusions. There are innumerable inclusions, but fortunately most of the inclusions are smaller in sizes. I had given an example that 1 kg of reasonably clean steel, I am talking of clean steel, not talking of dirty steel, they contain as high as 10 to the power 8 NMIs. So, you can imagine how many non-metallic inclusions are present in 1 kg of reasonably clean steel. Fortunately, most of the inclusions, 99.99% or more of it, are of smaller size. Only about 400 are of the 80 to 130 micron size. Only about 10 are 130 to 200 micron size. Only the probability of having only one large inclusion in this 1 kg of steel of having size 200 to 270 micron size. So, that means most of the inclusions are very small in size and hence they are benign, that means they are less harmful. So, we need not really bother about those very fine inclusions. What we have to bother about is a few large NMIs which are really harmful from the quality point of view. By large, I am again repeating, we are meaning more than 50 micron size, 50. That means inclusions which are larger than 50 micron, they are really harmful and we have to be very careful about those. But incidentally, I must mention that detection of these few, rather very few macro inclusions in steel is really difficult. Now, today I will discuss how inclusions are detected in steel, what are the different ways, how small small inclusions or micro inclusions can be detected, how macro inclusions can be detected, which are very difficult I have told, but how they can be detected. Now, let us go one by one to these aspects. I am now talking about evaluation of residuals and NMIs. First, let me talk about what is the process route, how steel is produced in commercial level or commercial scale. It can be two broad routes for the production of normal grades of steel. One is the blast furnace, basic oxygen furnace, and then secondary refining and casting. One is this route. Another is DRI, that means direct reduction iron, electric arc furnace, and then secondary refining and continuous casting. So, the before secondary refining, which is actually the ladle metallurgy part of the steel, where you can do a lot of refining, lot of quality improvement in steel. We have two broad categories, either blast furnace BOF route or direct reduction iron, which is also known as sponge iron, and electric arc furnace route. Finally, of course, we have to do whether we are producing steel by BOF or DRI-EAF, the final processing has to be secondary refining or ladle metallurgy, and of course, the steel has to be finally cast, whether through ingot route or through continuous casting route. Now, when we are talking of quality of steel, we have to put emphasis on secondary refining and casting, because most of the refining is possible only at these stages. So, let us try to understand where from we will get the samples for quality evaluation. Obviously, we have to take the samples from the final stages of refining or during casting if it is possible. So, let us see what are the stages. Normally, samples for evaluation of quality are taken from liquid steel, that means liquid steel in the ladle. If it is done through continuous casting, it can be taken from tundish, or in certain cases it can be taken from the mold also. If it is necessary to evaluate what is the quality level of liquid steel in mold, it is possible. So, liquid steel evaluation, if you are interested in, we can take samples either from the ladle, from the tundish, or from the mold. How the liquid steel sample is taken? We can take a small cup of or a cylinder of steel, using which we can take a liquid steel sample. It has to be immersed in the liquid bath. We have to be careful that we take a homogeneous part of the liquid steel. So, it has to be slightly interior in the bath, not exactly at the top, not at the bottom, somewhere in between. We have to take the liquid steel sample. We can take solid steel sample also. Where from we have to take the sample then? We have to take from the cast slab or bloom or billet. That means, once the slab has been cast or the bloom or the billet has been cast, we can cut small pieces from the slab, bloom or billet. Again, we have to be careful That's it. Samples have to be not from the top, not from the bottom of surface, but somewhere from in between. So, there is a process of taking the sample. Again, if you are interested in evaluating the quality of the final product, then we can take sample, solid sample obviously, from the final product. Final product means it can be a hot rolled product, it can be a hot rolled plate, it can be a hot rolled coil, it can be a forged product, forging, it can be even cold rolled steel. We can take samples from those products and evaluate. So, basically for evaluation of residuals and NMIs, samples can be taken either from the liquid stage, obviously from the final stage of refining, because I mean that is the final stage where the quality has more or less come to a particular level. Before that, we cannot take the samples before that, because after that many refining actions will be there. So, we will be interested in getting the quality at the final stage of the refining. So, we take samples either from the ladle or tundish or mold, basically the liquid steel sample I am talking of at these levels, or we can take cast slab or bloom or billet samples, we can take samples from the final product as well. Now, let us try to understand how do we evaluate. This is very important. We have taken samples, we have been careful, the samples represent a homogeneous mass, whether from the liquid or from the solid or from the final product. We have ensured the samples are not from the surfaces, it is from the interior, whether it is liquid or solid. Now, let us come to the different aspects of quality, which I have already covered. For example, if you are interested in knowing what are the sulfur and phosphorus, where from we get information on these two elements? These are part of the routine steel analysis. Steel is analyzed at the stage of preparation of the sample from liquid steel. That means sample is taken from liquid steel, sample is prepared very fast, and then they are evaluated by XRF or maybe optical emission. Nowadays, there is facility for online evaluation, it is very fast. Sample is taken, it is just some surface is polished to get a good reading, and immediately analysis can be done. So, as I was telling you, sulfur and phosphorus, which are very two important residuals in steel, we can get information in this information about these two elements from routine steel analysis, which covered sulfur and phosphorus. Now, I have told you that total oxygen is a very important parameter, which normally we do not measure in routine steel analysis, but from the quality point of view, total oxygen should be measured, particularly for evaluating the oxide cleanliness of steel. So, how can it be done? Using small machined samples. What do I mean by this? From the samples which are taken for routine steel analysis, we can cut small samples and then machine those, say the diameter may be 5 millimeter and the length may be 5 to 10 millimeter. That means a cylindrical samples. Small cylindrical samples can be machined, which can be analyzed by oxygen nitrogen analyzer. We can analyze both total oxygen and total nitrogen from this analysis. So, total oxygen and total nitrogen can be analyzed using very small cylindrical samples, which are machined from samples we have collected either from the liquid steel or from the solid steel. These evaluations, that means this determination of total oxygen and nitrogen can be done through oxygen nitrogen analyzer. It is a is a very common analytical tool for evaluation of quality, and we must use this for evaluation of total oxygen and total nitrogen in steel. One thing we have to keep in mind here, when we are preparing machined samples, we have to be careful that during machining the sample does not get heated up. Then what is going to happen is we are going to oxidize the steel samples, small samples. Oxidizing means we are unnecessarily creating more oxygen in steel. So, if you analyze your oxidized sample, whatever readings we will get will be erroneous. It will not reflect the real total oxygen in the sample, because we have additionally put some oxygen in the steel. So, we have to be careful not to heat up the samples during machining. In this regard, there is no change in nitrogen. When sample is getting heated up, we increase the total oxygen in steel because of oxidation, but there is no nitrogenation of the steel. So, nitrogen remains same. So, from nitrogen analysis also we can understand before and after, like if you machine it too much, if the sample gets heated up, we will find that oxygen readings is going up, but nitrogen reading does not increase. So, that gives an indication that there has been some increase in oxygen during machining. So, we have to be careful about that, so that we do not get an erroneous result. Now, how do you evaluate inclusions? I have talked about micro inclusions, which are small in size, say about less than 10 micron in size. Obviously, we cannot see this with normal eye, we have to use optical microscope. So, how do we see micro inclusions under optical microscope? We have to polish the surface, so that there are no aberrations on the surface. The surface is like mirror, we call it a mirror finish. So, if you polish the surface in this fashion, we can really see micro inclusions in the sample. Now, for looking at macro inclusion, as I have told you, macro inclusions are very few in numbers. So, we can see innumerable micro inclusions under microscope, but there will be possibly very few, or we may not even find macro inclusions under microscope. So, what do we do? What is the way? There is a technique called slime extraction. That means the steel sample, whatever the machined steel sample, whatever has been taken from the either liquid steel or solid steel, after machining it is slightly bigger than samples for oxygen, nitrogen. So, these samples can be electrolyzed, which is called slime extraction. So, after electrolysis, what will be electrolyzed? The steel will be taken into the solution in the electrolytic solution, and what will remain as slime are the macro inclusions. So, those slime after extraction, we can see those under different evaluation techniques, like under maybe we can use SEM to find out what are the constituents. We can see those at low magnification under microscope to find out what are the sizes. These are the techniques of using macro inclusions. So, we should know what are the macro inclusions, that means their constituents, chemistry, chemical constituents, and what are the size distributions. Likewise, for micro inclusions as well, we should know what are the type of inclusions and what are the size distributions. Now, as I was talking about, we should know the type of inclusions or the chemistry of inclusions, whether micro or macro. How do we do that? There is a technique called X-ray analysis using wavelength dispersion or energy dispersion. There are attachments, these are attachments in SEM. SEM is scanning electron microscopes. When we put the samples under scanning electron microscope, we can see the normal secondary electron images. We can also see, or also rather evaluate, what are the elements present. We can always also know what are the elements present in those inclusions by these attachments, wavelength dispersive and energy dispersive of X-ray attachments. Basically, what is the technique? Whenever electron is falling on the samples in scanning electron microscope, X-rays, elemental X-rays are also getting generated. So, depending on what are the elements present in the samples, we have different wavelengths. For example, if you have calcium in the sample, like I have told you, calcium oxide is a very common NMI, non-metallic inclusion in steel. Like if you have a slag sample, we may have calcium oxide in it to a certain extent. So, whether there is calcium in the sample, we can get from this attachment there will be a typical wavelength of calcium, either from the wavelength or the energy of that whatever X-ray is getting generated. If we catch those X-ray, if we detect those X-ray, either we identify the wavelength or the energy of the X-ray, we know what are the elements present, because every element will have different wavelength of X-rays which are getting generated. So, this is very, very important. This technique has been used extensively in recent years to identify the type of elements, and from that we can find out what are the constituents. Like if we know that calcium is present, oxygen is present, we know it is calcium oxide. If we know fluorine is present, calcium is present, and we know to what extent they are present, we know it is calcium fluoride. Similarly, all constituents can be evaluated. We can get an idea of, even quantitative idea, if we have a standard samples, like how much of calcium oxide is present. Not only the qualitative point of view, from the qualitative point of view, quantitatively also we can identify how much of these constituents are present in inclusions. Even in case of surface defects, as I had told you, the defects, if the inclusions are more in number, large in size, they can show up at the surface of the product as a defect, either as a crack or there may be a entrapment coming up to the surface. So, we can know what are the constituents present using this technique. We have to make a small sample from that, preserving the constituents, they should not get damaged, and then we analyze. So, under evaluation methods, sulfur phosphorus we can get from routine steel analysis. We know what is the phosphorus. If it is less than 0.15 or 0.25, sulfur how much is it, whether it is 0.05, 0.08, 0.10. If sulfur is low, less than 0.05, we know sulfur will be less. If phosphorus is low, we know that the deleterious effect of phosphorus will be much less in the steel. We know what is the total oxygen from oxygen nitrogen analyzer, we know what is the total nitrogen. So, we know how much of oxide cleanliness actually we should get in the sample, in the final product. Micro inclusions we can observe under optical microscope. Macro inclusions we can observe using slime extraction, that means through electrolysis process, and we know what are the constituents using WDX or EDS attachments of scanning electron microscope. So, these are the different techniques by which we can evaluate the different quality parameters in steel, whether these are sulfur phosphorus, that means the the quantity of the residuals, or oxygen nitrogen, how much total oxygen is present, whether it is the inclusions, we know their sizes, we know what are the inclusions, we know what are the size distributions, we know their quantitative value, whether it is the volume fraction is less than 0.1, we call it a clean steel, or it is more, then we call it is a relatively dirty steel, unclean steel. So, what are these parameters? We must evaluate this to understand quantitatively what is the level of quality in the steel we are talking about, and then we decide whether this is okay for the particular application or not. Now, we should remember certain important issues during this evaluation. Whatever data we are getting from these evaluations, we have to be very careful about those for analyzing these data. First, I have talked to you that when you are evaluating micro inclusions under optical microscope or any inclusion under optical microscope, what we are getting is basically a 2D, two-dimensional image, because basically we are looking at a surface. Maybe we have to look at 100 surfaces to get an average, but still it is a surface, two-dimensional surface. So, how do you know what is the distribution of inclusion in the bulk of the sample, in the volume of the sample? So, it is necessary to convert this two-dimensional distribution to three-dimensional distribution, which is more realistic. We should be getting more information about the three-dimensional distribution of inclusions in steel. So, by a simple relationship, this is the relationship, we can convert the two-dimensional distribution which is normally obtained through optical microscopic observation to a more realistic three-dimensional information. Like how is it done? This N2D is basically the number of inclusions per square millimeter of the sample we are looking at, sample surface we are looking at. So, if you want to know what is the three-dimensional, that means what is the number of inclusions per cubic meter, we can use this N2D value by dividing it with the inclusion diameter, which is by, let us take an average inclusion diameter. This dP is the inclusion diameter in micrometer. So, dividing this N2D by dP and multiplying it 10 to the power 12, this is the conversion factor, we can get the three-dimensional number of inclusions per cubic meter. So, what I am trying to tell? Let us take a particular size of inclusion, say 60 millimeters, some 60 to 65 millimeter range. We have got a distribution, a number in the two-dimensional observation. Now, what should be this number in three dimension for this 60 to 70 millimeter dia size? So, let us take an average, that means 60 to 70, average is 65. We divide the number of 2D, N2D divided by this and multiply it 10 to the 12, we get the number of inclusions of this average diameter in a in a sample of 1 micrometer. So, by this way we can get, this is square micrometer, this is not millimeter. Okay. So, by this way we know what are the three-dimensional figures, which is a more realistic figure. Now, let us try to go into some other issues. We have talked about how these inclusions, whether it is micro or macro, can be evaluated. But this observation of this shape is also very important. I have talked about the number, the sizes, but mostly they are not necessarily always spherical. In liquid steel, these are spherical, of course, but when you are deforming the steel, that means when you are using a rolled steel or a forged steel, we will get inclusions of different shapes. Even under liquid steel, all inclusions are not of spherical shape. Like certain inclusions they might be having a different shape, might be having a triangular shape, trapezoidal shape, and so on and so forth. So, what is important? To identify the shape also, the content, that means the volume fraction, the size distribution, what are the numbers for a particular sizes of this micro inclusion under the microscope of the macro by slime extraction. But if this evaluation, we have to keep in mind these are very, very time consuming. What do I mean? Like we have taken the samples, we have polished the samples, we have put it in the microscope, maybe we have to look at 100 different surfaces to get a realistic view, to get a statistical view. This electrolysis for macro and inclusions by slime extraction technique takes a lot of time. So, all these techniques are useful, but they are time consuming. These are essentially post-mortem analysis. That means the steel has already been made, it has been processed. After that only we are getting what is the level of quality. Is it really useful? Maybe yes, once the steel has been made, once the steel has performed in service, maybe we want to know if it has not performed well, what was the problem, then it is useful. So, it is basically sort of post-mortem analysis. That means after the steel has been made, it has been processed, then it has been made into a product, we are trying to get the information. Because this is a time taking process, we do not know when the steel is under preparation or under refining, under casting, under rolling, we do not know, we do not get these results. So, these are time consuming, but in contrast analysis of sulfur as element or total oxygen is very fast, because as I had told you earlier, nowadays even online analysis is possible for these elements. That means, when the steel is under processing, that means when the steel is even getting cast, we can get this analysis. So, we know from this first analysis of sulfur and total oxygen, what will be the possibility of getting sulphide inclusion in that steel, what will be the possibility of getting oxide cleanliness in that steel. So, when the steel is cast, by that time we have the information. Casting will take, maybe say it can take from half an hour to maybe 1.5 hours. So, during this casting itself, by the time we had finished casting, all this information on sulfur and total oxygen will be available to the steel maker. So, at that stage of steel casting, the steel maker knows what is the possibility of quality in that cast. What will be the level of sulphide inclusion, what is the level of total oxygen. I am talking of total oxygen here. It does not matter in which form oxide is present. It may be alumina, it may be CaO, it may be MnO, it may be anything. So, total oxide inclusion we can get an idea from total oxygen, as I have told earlier. So, this is a very fast, and we can get this information by the time steel is getting cast. So, if we find that total oxygen sulfur is beyond the ranges which are stipulated for the particular product, we can decide whether this slab or this bloom or this billet, whether at all we should process for the subsequent product, because these are going to give us very undesirable quality. These elements, analysis of these elements, sulfur and total oxygen, give us indication what is the level of quality. Unlike this analysis of inclusion, or whether it is micro or macro, which are time consuming, which takes a lot of time. So, when the steel has been cast, we do not know what is the level of inclusions, real inclusions, we have not evaluated. It is not possible to get the analysis by that time, but the sulfur and total oxygen analysis we already have by the time the steel is cast. So, we know whether the steel will be relatively clean or relatively unclean. So, we can take a decision at this stage, we can take a disposition decision, that means whether this slab or this bloom or this billet should be processed for this product or should be processed for some other inferior product, quality of inferior steel. Like no steel is thrown away. If the steel is relatively inferior in quality, it can be processed for a particular quality requirement, where a particular level of application is, the level of quality is tolerable, but that quality may not be tolerable for a very stringent application. So, a disposition decision can be taken based on the analysis of sulfur and total oxygen in the cast steel. This aspect is very important, and good steel makers nowadays are taking these decisions on quality based on analysis of sulfur and total oxygen. They are not waiting for the analysis or the evaluation of the inclusions, which will take a lot of time. They are taking decision based on sulfur and total oxygen in the steel. So, we can decide whether this steel, which is still in the cast stage, which has not been processed, whether we process it, because we know that this particular steel or the product will not give rise to good quality. So, it will not fulfill the stringent requirements. So, what is the point in processing this cast steel? Rather, we should process it for some inferior quality of steel. There is always as I have told, there is always a particular steel applications depending on the quality. So, we can take a decision on disposition of that particular steel cast depending on how much of sulfur, how much of total oxygen we have obtained. Therefore, the sulfur and total oxygen are used for a quick decision on the level of quality in the cast steel. This is very, very important. We have to keep in mind that all decisions nowadays are taken based on this sulfur and total oxygen at the stage of cast itself. We do not wait for the steel to be processed and then we get a very bad quality on the surface, because we know if the sulfur is high or the total oxygen is high, or even the if the sulfur is low but the total oxygen is high, that means the oxide cleanliness will be poor. If the sulfur is more, total oxygen is less, that means sulfide inclusions will be poor. So, we know from this data what is going to be the quality. So, we take a decision at this stage itself. I am trying to harp on this because please remember, at this stage only we have to take a decision. We should not allow expensive processing of the steel and then come to the conclusion that okay, this steel, this product does not have the requisite quality. We take a decision beforehand, before the steel has been rolled or processed. I think you should appreciate the importance of this decision.